Good morning, this is your Stat Sensei, Mr. Spensei, and this is going to be a reaction time scenario. We're going to be conducting a paired hypothesis test. So Professor Andy McNeil measured the time in seconds required to catch the following meter stick for 12 randomly selected students, dominant hand and non-dominant hand. All right, so they measured them twice. Whenever you measure something twice, it's going to be a paired test. Professor McNeil claims that the reaction time in an individual's dominant hand is less than the reaction time in the non-dominant. So they're saying D is less than non-dominant. Professor McNeil has 220 students. The difference in reaction times are normally distributed. All right, so they told us they were normally distributed. I'm going to act like in my problem that they weren't, but since they told me they're normally distributed, I can actually use that in my conditions. But here we go. So I have each student one measured twice, student two measured twice. So I'd put that data into stat edit, and there it is, L1 and L2. And to get L3, let me go back to stat edit, go clear that out. To get the difference, I just go to blue button 1 minus blue button 2 and press enter. There we go. And it did the subtraction all for me all the way down. Okay, since we're testing things twice, this is a paired test. And my formula for a paired test is T equals X bar D minus mu D SD divided by the square root of N. Please remember all hypothesis tests are centered on the mean. And when you're doing a paired test, it's assumed that the difference is zero. So HO mu D equals zero. That's our claim that there is no difference. But when I ran the test, stat test, t test, and I know I'm skipping ahead, but I'm going to go ahead and do that. Data is in zero. We already said that we're going to have an alternative of less than. Really important that we have that. And I end up getting a an X bar of negative 0.013. So it's not zero, it's negative 0.013. That's a small value, but there it is. Okay, so that's my drawing, and I have my less than. Make sure you list all your important information, the mean of the differences, the standard deviation of the differences, and X bar D, and my sample size. So I have everything listed. We've previously said the null hypothesis is that there's no difference. The alternative, well, he said that it was faster. So the dominant hand took less time than the non-dominant. That's the claim. So the mean of the difference is less than zero. Just going dominant minus non-dominant tells me the order. So I need to define my parameter. Let mu D equal the true population mean of the differences in reaction time, dominant minus non-dominant. You always have to tell the order that you subtracted it. Also, we need to name the test. Naming the test, this is a one sample paired t-test. And really for means. One sample paired t-test for means. All right, our conditions. Well, we have a random sample of 12. That was given to us. That was nice of them. And 12 times 10 is 120. And he had 220 students. So N is less than 10% of the population. So that condition is met. All right, they told us it was normal. So I can sit there and go, you know what? Normal. It was given to me. We're good to go. But because this one had an ugly box plot, I wanted to talk to you about the box plot. But I could have just put normal given because they told me it was. So I have my data entered in the calculator, second stat plot, press enter. So select the box plot with the outliers. Blue button 3, because that's where the differences are stored. And then presume followed by the number 9. And I get this box plot, and I can clearly look at it and go, you know what? It's weird. This part's stretched, this part's squished together, that part's squished together, that's a little stretch. But if I look at this versus this, those are almost the same. So from here to here is about the same. So consequently, it's not excessively skewed. So if you get something like that, label it up, difference in reaction times. The distribution shows no outliers or extreme skewness. Is there some skewness? Maybe. And we're going to sit there and say it appears normal enough. So if that happens to you, please, please run the test anyway. If you say it's too extreme, that's fine. You can go ahead and say it, run the test with caution, but you've got to run the test. All right. Please run the test regardless how the data looks. All right. So I'm plugging in my values into the formula. So showing my work. And all I did was plug in 0 for the mean, this for the standard deviation, this for the X bar D, this for the sample size. And please note, on a multiple choice test, they may cover up that 0, and it's going to look kind of funny because that's not going to show up. Because you really don't need to show the subtraction of 0. When I run the test, stat test, t-test, mean is 0, blue button 3 for L3. We said it was going to be a less than, so we have that shown, and we calculate. I get a t-statistic of negative 2.7759. Well, the probability that the t is less than that gives me 0.0090. And I'm going to take just a moment and we're going to go ahead and rerun it. This time I want to rerun it showing you a picture from the calculator. I'm going to change the color from blue. I guess red will show up, I hope. Oops. Instead of calculate, I'm going to ask it to draw. And there we have it. And you can't hardly see it, but right there in the corner, we see where our test statistic is. And we have our p-value down low. And we also have our t-statistic. So there it is. So there's our p-value, which is 0.0090. They told us we had an alpha of 0.0500. So our decision is to reject the null. All right. Anytime the p is low, the ho's got to go. If we have a small p-value, we have to reject the null. All right. We have to reject HO. So our p-value is 0.0090, which is less than our alpha 0.05. We reject the null. There is sufficient evidence to suggest the true population mean of the differences in reaction time, dominant minus non-dominant, is less than 0. Please remember, this right here is just a restatement of our parameter. This right here is less than 0. That's just placing our alternative hypothesis in words, less than 0. Okay? All right. So then it says, give the meaning of the p-value in context of the scenario. While you won't get points for this part of it, being able to state this lets the reader know that you know what you're talking about. And a lot of times you're given grace if you don't have things worded perfectly. So please make the statement. P-value is the probability of getting a test statistic this extreme or more extreme given the null is true. So in other words, given a true null, this is our probability that we'd get a test statistic like this. We're not proving anything. We're just saying, hey, if it were true, we would expect this to happen. This is where you're going to get the points. If there is no difference in reaction time, or given there is no difference in reaction time, that's what we said here. There is no difference in reaction time. Given there's no difference in reaction time, there's a 0.0090 probability of getting a test statistic of negative 2.759, which is what ours was, or less, because that's what we have our inequality is, less than, right here, because we have it less than, that's what we have it on our alternative. This is tied to the alternative. To use red for that. By random chance alone. In other words, we know every sample is going to vary. So by random chance alone, there is going to be some variation. And by random chance alone, we would expect this to happen 0.0090 probability or 0.9% of the time if there really was no difference in reaction time. All right, I sure hope this helps. Look forward to seeing you on the next one, and thanks for watching.